Hello, everyone. I would like to welcome you to the first Harvard Quantum Optics Center seminar this year. And our speaker, David Wineland, who we can welcome back here essentially because he did his PhD here actually with Norman Ramsey quite some time ago on the deuterium maser, and after that he worked with Hans Demelt on ion trapping and electron trapping, and then in 1975 he went to NIST, where he started his group on ion trapping, and he did spectacular experiments, as you all know, since then. Like, for example, in 1978 he did the first laser cooling. Then in 1995 a deterministic single ion quantum gate, and then entanglement between two ions a few years later, entanglement between four ions, and so on. And as you all know, there were these spectacular field opening quantum information, like quantum computing kind of experiments, and even some experiment on quantum teleportation, but also on applications of quantum information, like what can you do with quantum information. So, for example, he did spectacular experiments how you can use that for improving the accuracy of a clock, essentially as an application of quantum information. He won many medals, like the Benjamin Franklin Medal and the National Medal of Science and the Nobel Prize, and last year, as you all know. We are very excited having you here, and we are very much looking forward to your talk, Dave. And we still have a few seats in front if you run out of seats in the back.
Thanks, Marcus. So actually, part of the reason it's a great pleasure to be back. As Marcus said, I was a student here from 65 to 70, but that's ancient history for most of you young people now. But anyway, part of the reason, or actually the main reason I'm here this week, is there's two workshops at ITAMP, and this one just is concluding today, and then there's a second one that deals more with how we might scale up these systems to do hopefully more interesting things. The organizers for this meeting were Chris Monroe and Peter Robel, and we, of course, really we have to give all our thanks to Hussein Sadeghipour from ITAMP, who's put things together, and the meeting is actually has been up there, and the following one will also be at ITAMP. Anyway, at both of these workshops, there's a lot of different topics we've been hearing about, and I can't do justice to what everybody's working on. I am going to focus a bit on simulation, simply because that's one of the hot topics, not only for ions but for a lot of neutral atoms and a lot of other people working with quantum systems. So just to summarize, I'm going to, at least for the students that may not have heard a lot of this stuff, I'm going to give an idea of the basic techniques we employ, how that allows to manipulate the states and make entangling gates. And as I say, I'll focus a bit on simulation just to give you an idea. One of the things that a lot of people are working on. I'll say a little bit about what we're doing to try to improve things, and say a little bit about the future. So, I mean, one thing to point out, of course, is there's just a very large number of groups that are working on aspects of quantum information, and this is just ion groups throughout the world. So you can see it's a very big enterprise now, and of course there's many atoms on neutral atoms and condensed matter systems, Josephson junction, quantum dots, and so on. So this is just one small piece of the puzzle. But it's worth noting that actually this, in '95, Peter Zoller and Ignacio Sirac it was really the first comprehensive proposal for how you might make a quantum computer, a quantum information processor. And although, there's been some improvements, but I think certainly worth keeping in mind that this basic idea that they had is what we've all been working on, and it's what stimulated this large number of groups in the field. So the basic setup we like to think about is where we have typically we use this kind of configuration of electrodes where we're using RF and static potentials, but basically all I need to think about is we make a effective 3D harmonic well. We typically make the well along this horizontal direction relatively weak. So if we put ions in there, they stack into a line. Now there's two areas that people are pursuing. One is to use optical transitions for our qubits. And example of that, I see I got cut off here. But anyway, the example of that is calcium ions, which this 729 nanometers is relevant for, and Rainer Blott's group in Innsbruck, and there's several other groups that have used this ion with great success. Starting out on these things several years ago, the only thing that you have to, or let me come back to that. So one way we can address these ions is we might poke laser beams on them, where we, in that picture there, we're addressing all the ions. We can also think about, coming in at an angle and only addressing one ion. And the purpose of single laser beams for these optical qubits is that, for example, on resonance, then we can drive basically spin rotations about think about the Bloch sphere, about the XY plane. One thing the Innsbruck group has been really successful at is to do one form of gate. The Z gate is just by detuning the laser beams, you can, through the AC Stark shift from this off-resonant laser beam, you can impose phase shifts on the qubits it's being focused on. So the only slight drawback of this is you need, for long computations and so on, you want to keep phase coherence of your laser beam and the qubit frequencies over long periods of time. And in fact, the relevant number that we may not quite need yet, but we're still shooting for, is to have relative phase precision of about 1/100th of a radian. So over a long computation, you want to preserve this phase coherence. The other choice that a lot of groups are working on is to use where the qubit transition is a RF or microwave frequency, and we typically think about hyperfine or Zeeman levels. And the way we address those are through 2-photon stimulated Raman transitions, where we can coherently excite these states just like we do with a single photon laser transition. And so in this, here's a couple of examples. Here's the typical wavelengths for some of the ions of choice are given there. And of course, the reason a lot of us started in this direction, as opposed to the laser case, what we can do is we can generate these two beams, say from just one beam, and we apply a modulator, maybe EOs or acousto-optic modulators to generate this different frequency. And of course, we control that with a microwave source. And so really all we need to do, we need high stability in the microwave source, but you can buy that off the shelf, as opposed to what you need for the laser transitions for the optical qubits. The penalty we pay there, though, is that even though we drive these transitions off resonance and we only go through a virtual level effectively, there is some amplitude in these excited states, and we have to worry about spontaneous Raman scattering, which will decohere any superpositions we've made down here. So this, in fact, is a problem that we always have to worry about. So just saying say a little bit about gates here. As I mentioned, Ignatius Rack and Peter Zoller were the ones who really came up with the first scheme, and the first scheme they came up with to do 2-qubit gates in particular relied on the fact that you really wanted to be fully in the quantum regime of the motion of trapped ions. I won't describe their gate, but I'll describe how motion comes into play in the gates that most of us use now. So that was a bit of a drawback, and there were some improvements later on, is that in some different gates, and this one I will describe, and the condition on exact quantum motion states is relaxed. All we need there is we need the extent of the ion motion to be much smaller than the effective wavelength, and this is called the Lamb-Dickey regime. I'll say a little bit more of that. So it turns out you'll see that we still need to get the ions very cold, so we use laser cooling, and ideally we want to cool to the ground state of motion, but they will work with some small amount of excitation in the motion. So I'll give you an idea of these geometric phase gates. So what you want to think about is, say for any motional mode, you can first just think about a single ion oscillating in one back and forth in one direction. And what we usually think about is we go to a phase space picture, and we're gonna go into a frame where where if the state is steady, then it sits in this stationary in this momentum position space. So this is meant to represent our wave function, and the way we're gonna make gates is to take advantage of the fact that if we displace this wave function in phase space, it turns out that if we make a closed loop where the wave function comes back on itself, basically what we'd end up doing is impressing a phase shift on the wave function through this. That's proportional to the area of the loop we enclose in phase space. So one example of a gate that we can use is this so-called phase gate, where what we want to do, if we have two qubits and we want to realize this truth table here, where and this is just one example of a phase gate, but this one works. And if we just put this pi/2 phase factor in front of these components of the wave function that have opposite spin, and then this truth table makes up a gate that is universal in the sense that if we just only use this, if we can use this type of gates on pairs of qubits and also the rotations, that is the sigma x, sigma y operators, then basically the theorists have shown us this allows us to do universal quantum computation. The tricky part, of course, is how do we invoke this phase gate? And the thing we need to use is optical dipole forces that are state dependent. And I'll just give an idea how that works here. So what you can think about is, first of all, think about a single ion in the trap, and we're going to consider its motion along this direction here. So what we're going to take advantage of again is if we detune laser beams from some optical transition, then the difference in the states pick up a phase which is proportional to the Stark shift of this laser, and what we want to use is the gradient of the Stark shift, which we can use to apply a force. So the typical configuration we might realize, say for, again, think of optical transitions. We might use two laser beams that are oriented like this, and the reason for that is, for example, if the frequencies are equal, then basically we set up a standing wave grading by the fact that the beams aren't collinear. And so what this pattern is meant to represent is regions of high and low intensity of the Stark shift due to the two beams acting together. So of course with this potential, this oscillating potential landscape through the Stark shift, then we know there's forces on the ion that are proportional to the gradient of this AC Stark energy shift. And so what we do, one way we can excite the motion is if we just detune the frequencies slightly, and this is meant to match the motion frequency of the ion, and we detune it for a reason I'll say in a minute. But anyway, this standing wave optical potential, we sweep across the ion, and then it feels an oscillating force as it feels the portions of different slope of this moving standing wave. And the way one of the key ingredients, of course, is that to realize this case is we want to have a case where we can make the force on say the upper state different than the opposite, or the other state in the qubit. What I've represented in this diagram here are the case where it might be relevant for hyperfine structure, where on the optical scale the qubit energy levels are pretty close together. So this just continuing with this picture, then what we want to do in this particular example is we're going to try to realize the truth table that I showed before, and although it's not necessary, it's simplest to consider the case where, say, the force in this optical potential on the spin up, the upper state, is equal and opposite to that on the spin down state. So, pardon me. So this is meant to represent our optical dipole potential, which is going to sweep across the ions. And so the key thing here in this example, there's other ways to do this, but in this example, we're going to consider that we're going to excite the motion in what we call the stretch mode, just the mode where the ions are oscillating in opposition. We can isolate that from the center mass mode, where they're oscillating back and forth together in this potential, simply because they're at a substantially different, those two modes are at substantially different frequencies. So again, what we're going to do is we're going to tune the difference frequency of those two laser beams to equal to this oscillation frequency, and we're going to detune it a little bit. And I'll say why in a second. So the basic idea is the following: for those states where the two spins of the ion are opposite, these are meant to represent our two ions. And what happens in this case is that since the force is equal and opposite for the two spin states, when they're at this point in the potentials, they're going to feel opposite forces, which then can excite this mode here. On the other hand, if they're both in the same state, say the spin down state, then they're going to feel the same force. That'll tend to excite the common motion, but of course that's off resonance and can be far enough off resonance so we basically don't excite that mode of motion. So that's the basic idea. And the reason we detune it is, again, we want to close this loop in phase space. So if in this example here, I'm assuming the ion, this is meant to represent the wave function for this mode in its ground state. And the reason we detune it, just like this would work for a classical oscillator, is that we're going to go around in phase space, and we want, of course, the wave function to overlap in position, the original position. And the reason for that is that during this transit around this circle, the spins are entangled with the motional state. But if we come back and complete this loop, then at the end of this process, then the motion becomes unentangled with the spin states. And then the rest of the trick is that we have to adjust the detuning and the intensity so that we close the loop and make the area of the loop such that we pick up this I phase shift, which is so this is essentially the truth table that I wrote down for this universal gate before. So basically what we're realizing in this process, just this truth table here, it's equivalent to realizing an operator which goes like this, which we call a ZZ gate, and it's basically has other words for it, controlled pi phase gate up to a overall rotation of the wave functions. But anyway, think about it, call it whatever you want. It satisfies this truth table here. Now we want, I come back to this thing, what we need to satisfy. We don't need to be in the ground state, but we do need, we want this excitation, this force to be linear throughout this. And to satisfy that, we want the motion amplitude throughout this excitation to be much less than the effective wavelength. The effective wavelength here is basically just the wavelength given by that moving standing wave, but in order to make it a reasonable size force, it's on the order of the optical wavelength. So we still need to employ laser cooling in these experiments, but we don't have to be exactly in the ground state. We can typically be in the first couple of excited states, and it doesn't matter then, as long as the wave function the overall wave function of that initial excitation doesn't change, we can close this loop and come back on itself. Just as a bit of an aside, if we get out of this limit here, then what happens is the force becomes nonlinear, and we tend to distort the shape of this thing. It becomes squeezed, but it won't overlap then when we complete the loop. Well, there's another form of this that actually these gates. Originally, the way they were proposed, they look quite a bit different, but they can be put in a common language. And this gate that we've tended to call the Molmer-Sorensen gate, because they had I think Molmer and Sorensen did the most development of the theoretical ideas originally. But it's basically this same gate, but the only difference is that we're going to operate on the plus x and minus x states, which are basically, in the block vector picture, it's states that are in the xy plane, but they're just superpositions then of the bare basis states. And the idea is very much this phase-based picture I just showed is very much the same, except we're operating on these basis states. In order to implement it, though, we need, in this case, we need two sidebands. For the optical transitions, the beams can be co-propagating, but we want to detune the sidebands. This is this detuning that appeared in the last few graphs, so that the wave functions come back on themselves. And we want to have laser beams, in this case, near both what we call the red sideband, the lower sideband, and the blue side. But anyway, the same picture then holds for this phase gate in these basis states here. Actually, for Rainer Blott's group has basically he's had the best system for quite a while, and this so with this. The gate that they realized, the phase gate in this basis here, the fidelity of this gate is a little over 99%. Actually, just today I learned this other gate that I first described. David Lucas's group in Oxford, they've been able to essentially get the same fidelity in this other type of gate. The other thing to say is that so these are kind of the gold standards of gate fidelities for anybody's implementation of a quantum computer, and I think that's why there is a lot of interest in what the ions can do, at least at this stage of the game. So there's also, we can do the same tricks with stimulated Raman transitions, a bit more complicated. In general, we need 4 laser beams. These two transitions then become stimulated Raman transitions. Now, in fact, we can economize a little bit. We can double up on one of these beams. But actually, one of the headaches we have to deal with is that for these types of gates here, the beams have to be separated by on the order of the hyperfine frequency, or twice the hyperfine frequency. And that doesn't sound like a big deal, but as a practical matter, where it becomes a big deal is we typically create these different frequencies of laser beams with acousto-optic modulators. And in practice, at least on the ultraviolet part of the spectrum, what that means is we got beams going through modulators. They're separated in space, and they tend to get phase shifts between the beams due to air currents and mechanical vibrations. So this is one of the headaches we deal with the hyperfine qubits, and why at least for these types of gates, why the fidelities aren't as high as what Reiner had achieved. So anyway, now I'm gonna you get an idea how this gate works. What you can think about is that it's implementing this for this so-called Molnar-Sorensen gate. It's implementing this Hamiltonian here, where it's basically a product of this two spins. So for two spins, it has this form here, and we can also one popular model that people are looking at it to simulate condensed matter systems. In this case, just for two spins, but we add a transverse magnetic field, and this for those familiar with this, basically we start the ions in either the up or down state, and then we do a pi over 2 rotation, and then we superimpose a field along the axis where the spin is pointing, and that will pin then the ions to the y, in this case the y axis. So this was first looked at by Tobias Schätz's group, but this has become a model system for the ions and neutral atom and other experiments to look at to try to simulate. So what I'm going to try to give you an idea kind of where the state of the art is. This is some data from Chris Monroe's group at Maryland. So I rotated the picture 90 degrees here, but what you want to think about is we have this walking standing wave that's moving down in this picture here. What we're going to do in this example is that we're going to think about the transverse modes. That is, in this picture here, the modes where the ions move in the plane vertically in this picture. And this data, I think maybe my ends got cut off here, but this was some data for 9 ions, and this would be the mode spectrum. So what this frequency over here, this represents the center mass mode, where all the ions are moving up and down together in the trap. This second mode is somewhat lower frequency, is the one where this string is tilting back and forth, and then there's other modes that complete the spectrum. But anyway, if you come back to this gate picture, it turns out that what we do is we tune our laser beams such that we make this walking standing wave if we make it very near this center mass mode, and what you can think about is we're just only then primarily going to excite the center mass mode, and these other modes, since they're detuned, will be excited very little. But to that, in that limit, then what we get is this type of interaction here, where it's a sum of this mutual spin-spin interaction between all the ions, with every ion with each ion with every other ions, and in fact one of the first demonstrations of these types of gates is where we could make so-called GHZ states. That's superpositions, where we start out with all the spins down, and we can make a superposition where they're equal superposition of all down and all up. But more generally, in this simulation context, what we can write, if we vary the detuning there, we can get a more general form of this spin-spin coupling. It turns out that since we're tuned above this resonance here, it turns out that these J values are positive, which simulates then an antiferromagnetic. That is, for the ions that are adjacent to each other, they want to be in opposite spin states to minimize the energy. So this is one of the interesting problems that we and other people are looking at to try to realize these ferromagnetic interactions. And it turns out by varying this detuning from these other modes, again, if we if we're very near this center of mass mode frequency, it turns out to realize this coupling, it's essentially infinite range. But if we vary the detuning, make this detuning larger, we relatively speak couple in more and more modes. And in fact, we can vary the range of this coupling along this string according to some power law. And I've forgotten Chris Monroe's experiments now, but it basically can go from where this alpha parameter is 0 up to about 3. So again, the more general form of this transverse Ising model then is where we have this general coupling, the spin-spin coupling, and then we can also think about imposing this effective magnetic field along the y-axis. And these are some of the proposals that dealt with how that transverse Ising model might be implemented. So this is again some of the data from Chris's group. In this case, it's 10 ions. And what they did in this experiment here is here's the Hamiltonian again. And what they did is they started out by in this block vector picture. You can think of all the spins being polarized along a magnetic field in the y direction. So they started this strength out fairly high. And then what they did is they ramped down the strength of this effective magnetic field down to 0. And of course, what happens then is the system wants to go from when the spins are all aligned, and because this J parameter is positive, they want to then flip around so that they realize this anti-ferromagnetic behavior. And Chris and his group has been able to realize what this. So I'm going to just some snapshots as this field is ramped down. What they do is they're basically they measure this correlation function here, and you're going to start to, as the ramp goes down, you can start to see zigzags in this correlation function. This is the sort of the correlation function between the first spin, which isn't shown here, and the rest of the spins. And the zigzag structure in this picture, in this correlation function, just shows the fact that this ferromagnetic structure is setting in. And so anyway, this is the kind of thing that Chris and his row, they've been able to do up to 16 ions now with this in these kind of experiments. One of the interesting things is that they can, of course, the data to be able to determine the spin states when we do the measurement, of course, we see the diagonal elements of the density matrix. So you say, well, in principle, this process in the perfect world would yield states that have coherence, but between all the elements of the individual qubit wave functions. And at least in this, there's other experiments that have been able to demonstrate this coherence. And they've done it in their experiment is just simply come down at this point here and then just reverse the evolution. And by looking at how much polarization they end back on the y-axis, they can show at least that that this process has been coherent. That is, it's not just population dynamics, that there's coherence in the wave functions that evolve in this system. And the other interesting thing in this, they can see what's called frustration, and the idea there is that if they vary the range of this force, make it long range, then this second spin, because of the anti-ferromagnetic interaction, it wants to be opposite spin of this ion over here. In this example here, the spins are correlated, but there is this frustration in that as they make it longer and longer range, this zigzag structure, these correlations tend to be diminished, and they can see that effect as well. So this work goes on. I think one thing that makes these experiments tough at this point is that the strength of these interactions is on the order of a kilohertz in these experiments. So this ramping has to be done relatively slow, or otherwise there's diabatic transitions in this process that make the results not as clean. So as I mentioned, they're up to 16 spins now, and they're trying to move up to 30 spins. And the interesting part about that is maybe around this range of 16 to 30. It's going to be impossible to simulate this on a classical computer because of the exponential scaling and in the resources you need to do the computation. So I think this is why a lot of us are excited now, is that these kind of systems are getting to the point now where we're going to have trouble doing the classical simulations. This is another example of the same kind of thing with ions. This is John Bollinger from our group, and his guys are looking at it. This is a different kind of trap, a Penning trap, which Jerry Gabrielsa works with here. But in this case, it's an array of ions. And what you want to think about, this is a circular array. For those that know about Penning traps, there's a magnetic field out of the board here. The ions are circulating around here at tens of kilohertz. By using stroboscopic means, we can freeze the motion. But one of the interesting things about in this experiment is, first of all, the number of spins that can come into play can be very large. We certainly can't simulate this system on a classical computer. The other thing is if you look at this lattice structure, it's kind of a triangular lattice structure, and there's sort of a natural spin frustration built into this for the antiferromagnetic interaction, where, say, if you consider these three ions here, this one wants to be anti-aligned relative to that one, but this one doesn't know what to do because it can't satisfy that condition for the other two ions. So in some ways, this frustration in the system is naturally built in. So John and his guys have also varied this by varying the detuning from this is again the center of mass. This is the tilt mode, just like in a 2D version rather than in the linear version that Chris realized. He's been able to vary the strength of this coupling, and also the coupling is, it turns out, about the same order of magnitude that Chris realized. And this experiment is just building up. So far, they haven't been able to see the correlations, but the attraction of pursuing this, of course, is this very large number of spins in this natural array where frustration can show up. And I feel I was going to try to say something about Rainer Blott's experiments at Innsbruck, but I'm off the hook here. He's going to give a colloquium this next Monday. It is up at ITAMP, isn't it, Rainer? I want to make sure I say this right. It's at the same place we've been? Yeah. Yeah, is that right? Okay. So up the street you'll need to go. But Rainer's done a whole host of interesting kinds of simulation experiments. But one thing that he's done, which I think is really a landmark in some ways, because it turns out that if we have a general Hamiltonian that might be a sum of several different interactions, of course it's hard to simulate, because if these Hamiltonians are non-commuting, you can't just write down e to the IHT to get to e to the IHT to get to the evolution. But one way this is done theoretically, and what they can realize experimentally, is basically if you take small steps in this Hamiltonian, that is, just let it evolve stepwise for each one of these Hamiltonians for a small step, and then just concatenate this process. So you divide the interaction time by the total interaction by times 10, and then just multiply this thing together n times. It turns out that the non-commuting terms, if you make n large enough, they can become small enough to simulate the evolution caused by this Hamiltonian. And Reinerson and his guys have done some demonstrations of this kind of trotterization, but I think more importantly, it's really, in a way, it's really a universal quantum computer. He can simulate any Hamiltonian with this process. And so I think this is also very exciting. The thing to say, I think, not to take anything away from experiments I mentioned here, is that I think we still want to work very hard to try to make higher and higher fidelities, get rid of the errors in the experiments. So we have a way to go on both fronts, working with larger numbers and also improving the the fidelity of the operations. And I should say I've listed a few other references, and I apologize. There's many others that I could have listed here, but I think these are representative of the kind of things we're trying to do in this simulation business. So I'm just going to say a few words about little pieces of this puzzle we've been working on lately. I mentioned John Bollinger's experiment. There's another approach here, which I'll mention in a second, that controls the geometries of these interacting spins potentially. I'll say a little bit about gates, since it's sort of it's kind of the nuts and bolts part in some sense. We've also been working on scaling, which this second workshop is about. I won't say much about that. And I'll conclude by saying some of the headaches we've had over decades now that we're starting to make inroads on. So in this other idea for simulating, the idea is that in this case, what you can do in John Bollinger's experiments, for example, that you might regard the arrays, those triangular arrays, are sort of self-assembled. That's what you get naturally of those triangular patterns. And another way to get arbitrary patterns is you might think of patterning electrodes such that you localize each individual ion in a certain place, and then you can make different kinds of arrays. And so this kind of idea we're not nearly as far along, but this is the kind of thing we're thinking about. And maybe as a first crude step in this process, what we've done, just done a 2-ion experiment here. There's been a similar experiment that I list there. But the idea here in this simple demonstration is we want to make two traps that are very close together, and then the ions, they simply can couple by a dipole interaction, which then can be used to simulate these spin-spin interactions. And kind of where we are right now is we've been able to get on the order of separations on the order of 40 microns, and for those, the couplings are again about the same strength as what Chris Monroe and John Bollinger, these mutual couplings. And what this experiment shows here is just some data where we would start put both the ions in their ground state of motion, and then we'd put one quantum in one ion, and we'd see this exchange going back and forth. So this is actually some improved results over what we got a couple of years ago. We've also been able to do a gate that is invoke this ZZ or XX interaction between two ions and separate traps. You can see the fidelity is not very good yet, but at least we're hoping that this might get us along the way in terms of making these arrays based on the geometry of the traps. And certainly we want to go smaller. We want to push the ions close together. This coupling goes as 1 over the separation to the third power. The reason we can't yet is that it turns out, I'll come back to this later, but in order to go smaller dimensions, we have to make the structures smaller, and we have to get the ions closer to the surface, and all of us suffer from a heating process as we bring the ions closer to the surface, which compromises any sort of quantum operations we might do. So let me just say that although this sounds like a dirty detail, one thing we've in the gates that in our experiments so far we've struggled to get above about 97% fidelity. So I come back to this so-called Molmer-Sorensen gate. This is the example based on in the case of optical transitions. So in that case, we need these two beams separated by roughly just twice the motion frequency of this mode that we're exciting to make the gate. And on the other hand, with a hyperfine, I already mentioned that in general, we need to have beams separated by twice the hyperfine frequency. And this sounds like a trivial thing, but it's hard, as I mentioned, just because it's much easier to separate these two sidebands or these two frequencies by megahertz as opposed to gigahertz frequencies. Now there is one way around that Chris Monroe has demonstrated, is he used two optical combs that are offset, and they can use I won't get the picture. They can use a tooth comb from one beam and then span the few gigahertz that he needs to by selecting another tooth comb, and then shifting them relatively with a small frequency shift with an AO modulator. The thing we've been trying to do, though, we've been trying to realize the same process again with acousto-optic modulators. So just to give a rough flavor of what we do, in this example here, which actually was proposed by Alejandro Bermudez and his colleagues, Alejandro's here at this meeting, there's some similar ideas based in the cavity QED context. But the basic idea, at least functionally, what we do is we're gonna make dress states, and the way we do that is we drive the carrier very hard. So the natural states then in that stress state basis are the ones, the plus and minus states, the same plus and minus states that I mentioned before. And it turns out, I won't go through all the gory detail, but this is the interaction we want to make this so-called Mulm or Sorensen phase gate. We do pick up other extra terms here. There's a spin flip term coupled to the motion, but it's detuned by basically the Rabi frequency of this transition. So the higher we can make this Rabi frequency, which addresses the states, the smaller this term becomes. And one of the nice things about this, as I say, it seems like a trivial detail, but it turns out that in this case where we have to keep both sidebands very phase coherent with respect to each other, and we're bothered when we're separated by gigahertz because of these phase fluctuations due to air currents and vibrations. In this case, we only need one beam. It doesn't have to be. It doesn't have to have any long-term phase relation with this carrier transition. It just has to be constant over the time of the gate, and that has turned out. It looks like it's going to be a pretty good thing. Whereas we still don't have high fidelity yet, but we think we know how we can do it. But just to give you an idea, if we drive this carrier transition with lasers, in this case, you see that these contributions to the error, the largest one is due to spontaneous emission, and that's just from the fact, in our case, we're driving this transition with spontaneous Raman transitions, and we get spontaneous emission. If we do it with microwaves, the error there can be quite a bit less. In this case, we didn't have a nice way to inject the microwave, but you can see the error is relatively small. We're left in this. This is just kind of embarrassing. We think that we can improve this a lot. We do have to again worry about this is long enough with the relatively slow strength of this carrier flopping that we have to wait long enough that we get some imperfections due to this background heating that I'll come back to. But anyway, we're hoping that might be a way in the future. So what a lot of us are doing now in order to shrink things down is that it's just hard to make things smaller using this conventional machining. So what we've done, in this cartoon here, I'm assuming we're looking down the axis of the system, and these are the four rods, and we can distort those into a plane and then have a trapping position above the planar electrodes. And the nice thing about this is, of course, we can make, using basically just relatively common microfabrication techniques, we can make the electrodes in a plane, and we can make them very small, actually. And there's a number of groups pursuing this idea here. So this is one example of this. So this is looking down on one of these planar structure. This is a surface electrode trap that is all the electrodes in the plane. And so I won't go into the details of the trapping here, but this shows just the blow up of 5 ions that we trapped. They're about 30 microns above the surface, and the spacing is on the order few microns. And what we can do, one way we can speed up these carrier transitions that would be useful in this gate I just described is we can put currents right next down, say, this electrode here. And then if we run currents, then the magnetic field is above the plane is going to be in that direction. We oscillate that to drive these spin-flip transitions. So what this data just shows here is a picture of the data from of this carrier flopping. And the typical times with laser beams on the order of, for a pi transition might be a few microseconds, and here we're down to about 10 nanoseconds, so we can really speed up these gate operations. The other reason we're thinking about trying to use microwaves as much as we can is that we're helped with speed here, but also just we can control microwaves much better than we can with laser beams, that is driving transitions with laser beams. And it basically has to do with intensity fluctuations. I remembered I mentioned this problem of intensity fluctuation that can be due to the beams waving around. It can be due to power fluctuation. But microwaves, we can do a much better job. And this shows one of our results. But basically, again, with the Oxford group, they've been able to show an error per operation of about 10 to the minus 6 now. And this is certainly the record in any of these kinds of experiments. So this is the big attraction for using microwaves, is just that we can control the amplitude, the intensities much better. So one thing we're doing, one thing we're trying to starting on, and we're trying to take advantage of, is if we, in this experiment here, what we're doing is we're trying to, at the position of the ions, we're trying to make a gradient field, which we would get from one wire, but we also get a field from that wire. So we use a combination of currents and phases in 3 wires. And what it means is we can null the field along the position of the ions, but make a strong gradient. And so in this case here, what we're trying to do is make a gradient that's transverse to the axis and do these kind of gates that we've done with laser beams that I showed you, for example, with Chris Monroe's experiments. And so we're not doing a very good job yet. And part of the reason is we would like it's just a matter of the gradients. The gradients, which then control the Rabi flopping rate, go as 1 over the dimension squared. We'd like to make things smaller, but we're stuck with this heating problem. So let me say a little bit about these problems we've had, and maybe we and other people are starting to make inroads on this. So this is a graph showing turns out for different ions and different trap structures, we can normalize these results, and there's a way to extract the electric field spectral density above the surface of the electrodes. And this is sort of a crude measure. It's just typically we use the distance of the ion to the nearest electrode to characterize things. Now this data, I mean, you could fit it to almost anything. I think there's on the other hand, there's a couple of things. I think at least there's certainly a contingent of us believe there's a model for fluctuating fields. We don't know what the source of these fields are. We do know that it's noise associated with the electrodes. One model that would fit this slope, this is not meant to be a fit, it's just meant to indicate a slope. One model that would describe this 1 over d to the 4th scaling is if you had, for example, if you had patches on the electrodes. They were small patches, and they were randomly fluctuating with respect to each other. That is, if they were small compared to the distance of the ion to the electrode, you get this scaling here. So some of us believe this, some of us don't, but nevertheless, but it's pretty clear that we do better when we make, we get worse heating when we get smaller electrodes, and we do want to make them small for the reasons I mentioned before. This data here shows experiments at low temperature. This is the first experiments below room temperature done by Chris Monroe. There's a lot of data taken by Ike Chuang at MIT. You clearly win there, and we certainly want to take advantage of that, but we'd like to understand this process in a fundamental way. You can see I'm running longer than I hope to, but let me just give you an idea. Actually, there's various models I think one of the most complete models is done by Hossein Sadeghipour here at ITAMP and his group, where they basically construct a complete model where they assume there's some adsorbates on the surface. They can be caught in the surface potential of the surface. They can be excited at different energy levels in this surface potential. That will change the dipole moment associated with this adsorbate atom or molecule, and thermal fluctuations can drive these excitations and cause oscillating dipoles. So they have this fairly complete model. So far, we can't quantitatively fit it, but it is a very complete model. There's some similar work done by Hartman-Hefner's group at Berkeley. There's actually an old model that comes to mind, and basically, 40 years, 50 years ago, studies were done on field emission. That is where you have a very small, sharp tip of typically tungsten. If you just charge it up, the curvature is so small that it rips electrons off. And these field emission currents, they could study diffusing atoms by just the fact that these atoms across the surface would cause fluctuations in the emission current. And so there's this model that maybe rather than atoms being excited locally in their potential, they may be diffusing around, which changes the work function. So these are the kind of models we're playing with, and we're not able to pin anything down yet, but this is what we're hoping to do. But anyway, this has been bothering us for decades, all the groups, I would say. And so we'd like to do this, so we're trying to collaborate with pros on this, and at NIST, these guys here are surface scientists, and so I think a lot of us thought about this for many years. We thought we had strong suspicions that it was stuff that was adsorbed on the surface. So a common technique the surface science guys use to use a few hundred volt or a kilovolt ion beam, which basically just scrubs the surface, just kicks the adsorbate atoms off, and so we did that. And the reason none of us did it until recently is just that these guns are just a pain to incorporate with these ion trap apparatus. They're not that big. They're maybe that long and a conflat flange diameter roughly, but it's just hard to incorporate with the apparatus. But anyway, what we did see, we saw a big improvement. And what we could, in these first crude experiments, we could correlate it. In our case, this was the surface, or rather copies of our surfaces treated the same way we do our traps. And we could see a carbon peak, meaning this is OJ's spectra here, where it indicated there was probably some hydrocarbon on the surface. And after this ion bombardment, the carbon was essentially absent, and these peaks here are due to the gold of the surface. So we could at least correlate this heating, or this reduction in the heating, with this removal of carbon-containing materials. And this was, anyway, we feel like we got a long ways to go. But this was the surface before treatment. This is after. So we reduced the heating by 2 orders of magnitude. One thing we always have to worry about is there's always, at a minimum, Johnson noise, just due to thermal electronic noise and any resistance associated with electrons. And in this experiment, we estimated it to be down here. So also, Hartman-Hefner's group has done some similar experiments, and they also see this similar improvement. So we have a long ways to go, but at least we think that maybe we'll make some inroads to improving the surfaces and making structures smaller. It'd be nice, this is also experiments done at Oxford, and they saw, with just using pulse lasers, they saw just a factor of 2 improvement. But this would be much nicer if we could get lasers or light of plasma discharge. Particularly with lasers, we already have windows in our system, and maybe we could, if we could use lasers to do this cleaning, that would be great. We wouldn't have to have any extra attachments. Anyway, we're trying to think of a more general way to attack this problem with help of our surface science colleagues. And so one approach we're pursuing is we made what we call a stylus trap. It looks pretty much like this, and we can hold an ion off the end of this thing. And the idea that this general plan that we're hoping to realize is we'll have all under vacuum. We'll have some test plate here that in this cartoon, we might do plasma cleaning or some deposition of some material, and then we'd move this into position and then measure the heating rate. And maybe we could cycle different procedures and different materials to try to make headway on this problem. So I see I'm about out of time, but let me add one other these little technical things that have been bothering us for decades is one of the problems with UV. So some of our favorite wavelengths for beryllium and magnesium are in the ultraviolet, near ultraviolet, 313 and 280 nanometers. And we would love to have optical fibers. The optical fibers in these experiments do two things. One is that we can, I mentioned earlier that when we do when we modulate the beams, we do it with acousto-optic modulators. In the UV, we've had to do this in free space. And the problem we end up with with all the modulations and switching we want to do, we end up with beam lines that are meters long, and we're bothered by vibrations and air currents. If we could launch the light from a fiber very near the trap, that would help us a lot in terms of that problem. The other thing is that just if we had single mode fibers, then these particularly when we use these acousto-optic modulators, the beams, they just aren't very nice looking. They don't look Gaussian at all. So we can we know in the visible we can do that with fibers. It gives single modes, and of course we can move the launch point up close to where the ions are. And this shows just some kind of the data we've always seen. In this example here, this is end-on a photonic bandgap fiber, but in this case it's solid core. But this is what we had seen for many, many years is you put UV light in and the UV forms color centers, which absorbs, and the things die after a few tens of hours, even at relatively low power. So, but anyway, one of our recent postdocs, Yves Coulomb, has come up with, at least to me, a magic recipe. And the idea here is that what he does is he takes fibers. These are, again, photonic bandgap, but solid core. And he saturates them with hydrogen just at room temperature, about 100 atmospheres for a week. And then he exposes them to the UV, the same UV we need. And at least the model is that they do make color centers, but apparently these color centers, they absorb at wavelengths that aren't of interest to us. And so anyway, with this, we're in the midst of this. There's a lot we don't know, but this is just an example. If we use the same fiber, but we didn't do this treatment, the transmission decays rapidly. But now we've been able to get hundreds of hours using this process, even with fairly high powers, up to, in this case over here, 50 milliwatts. So we're really hopeful with this thing, and of course we're gaining now this. It really cleans up the mode here. So we have our fingers crossed that we might be able to use this. I should also mention Pete Schmidt in collaboration with Philip Russell at Erlangen, and they're actually also using photonic bandgap fibers. In their case, to get rid of the loss, they use a hollow core, and I mean they're getting some interesting results. The one thing that's nice about these, just in fact, a fact about with these solid core fibers, the transmission is relatively insensitive to bending of the fibers, whereas it is a problem with these hollow core fibers. Okay, so that's it. I just want to say, at least for the near term, I mentioned these things we're hoping we're making some improvement on. So we want to incorporate these cleaning techniques into some of our next round of experiments, and also the fibers. I think in general for all of us, we do want better fidelity one way or the other. We want to play with more and more qubits, particularly get to this region where we can't actually simulate it anymore on a classical computer. we and other people think about how to couple Orions to other quantum systems. And one of the certainly new hot topics with a lot of young good guys coming up is to extend some of these ideas to doing molecular spectroscopy. And there's many other things here that I haven't mentioned. So with that, of course, I want to thank the people that really did in our group, the people that really did the work. This is our group from last March. And with that, I'll stop. Thank you.
Yeah, thank you very much. Questions? Mm-hmm.
For the general architecture of this future quantum computer, would you say a planar arrangement is a must, or could it be three-dimensional or linear? What is your personal preference?
I don't.
Choose one or the other.
I think choose your poison. I don't know. I mean, certainly there's some obvious advantages of 2D versus 3D, and then you can rearrange things in much more straightforward way. 3D is also interesting for the same reason, but you can imagine it's hard to thread laser beams through a 3D structure and do the detection of the right places and so on. But you could have said that, so I don't think there's any obvious way.
Another question? Mm-hmm. So I have one quick question. So the hydrogen, the
Hydrogen loading, yeah.
But the hydrogen actually diffuses into the glass essentially, and
Yeah,
then,
yeah. And in fact, what's interesting, it seems to, we don't know, but it may just act as a catalyst somehow, or it may actually go in to part of how these color centers are formed. But we do know, for example, one test, it is important. So we can take our hydrogen-loaded fibers. If we then bake them, so assuming the hydrogen comes out, then we get this old results. If we do the UV treatment first and then we bake them, they're still good. So somehow the hydrogen is important to whatever color centers are made.
Another question? Yeah, if not, then let's thank Dave again. For a great talk.